Hello, science lovers. Here we are today on a kind of rainy day in late October. Scott's going to talk about stars today. He's coming up to the podium now, and interesting topic, and I'm looking forward to it. I've got some interesting news. I have my daughter out in Seattle. I think they're on their way to the hospital now with the baby granddaughter for Jane and me coming due sometime today. So if you see me kind of hopping around in my seat or something like that, then maybe some news came through on my cell phone. But other than that, we are here for Science Sunday, and it's a week later than usual. This is the fourth Sunday in October, but that's the way the timing worked out. Scott is actually going to be handling the next one for me. The first one in November, first week in November, I believe it's the 6th, and because I'll be out in October to make introductions with my new grandchild at that time.
Mike, is there any particular program you'd like me to talk about while you're gone, or subject?
Just cover all the science.
Yeah.
Yeah.
Okay. All right. I'll do all
We've
that.
got a few guests and a bit of a studio audience in here. You might have just heard a little hello from Darwin. A nice support dog for all of us here. It is Scott and Dave's dog that's here visiting today. And my son is in from New York, from Washington, D.C. with his fiancée, so they are going to be in the audience too, I think, in a few minutes. So it's kind of nice to have some people in the audience, and we've always tried to open it up in the last while to have people come in. If you're interested, you can contact me, and I'll authorize to try to keep numbers to a small amount, 10 or less in the auditorium here.
You want to talk about how to get on the mailing notifications you send out?
Yeah, if you want to hear and you haven't been hearing from me on email, it's 19mike55@comcast.net. 19mike55@comcast.net. If you just send me a message, I'll let you know that what's coming on. I try not to send out too many messages, just one announcing each discussion topic and just letting you know and be sure about times and dates and so on. So hopefully you're excited about stars, and if you're not, you probably will be by the end of this, because I think it's a fascinating topic. So without any further ado, I'll hand it over to Scott. We'll be open on Scott's laptop. You can go on the live stream and make comments. And
you're already probably watching live on YouTube, so you can just type in your comments or questions, and we'll take care of it.
All right. And it looks like you got a Starry Night mask on, too, so that's appropriate. All right. Thanks a lot.
I wear this mask in recognition of the wonderful contributions of Neil deGrasse Tyson. He says this is his favorite painting, Starry Night. And also because I happen to love stars as well. So welcome to everybody. This program wouldn't happen without the support, both practical and in terms of friendship and encouragement from the DuPage Unitarian Church and the community of the church. Also, this is co-sponsored by the Prairie State Humanists. And you can check us out on meetup.com. We've got a meetup page for the Prairie State Humanists, and you're welcome to check that out. So again, we have our dog with us. We've had some personal issues in our family, Dave and I, and Darwin is with us, providing companionship and also to keep him from being very anxious about our absence. So I hope that if Darwin makes comments or asks questions during the show, I hope that doesn't disturb anyone. So without further ado, I'd like to talk about the first stars in the universe. This is a drama in 3 acts. So hopefully not one of those kinds of dramas where there's going to be, murders and stuff like that. This is
there's some deaths, probably.
There will be some deaths of some fairly famous stars. And in honor of our approach to this Science Sunday, Each act will be preceded with a quote from the bard himself. And this first act is, "All these stars, numberless and eternal, not from the stars do I my judgment pluck, and yet methinks I have astronomy, but not to tell of good or evil luck." It's a pretty interesting sentiment there. We're not, astrology, which this is alluding to, the science of, the pseudo-science of astrology, was the precursor to the science of astronomy. And astronomy has been studied for hundreds of years in a concerted, scientific way. And what I'm going to be talking about today are some of the more remarkable discoveries and conclusions about the science of astronomy. So I'm going to begin with a little narrative that I've written up, and then we'll move on to the rest of the program. Stars seem mysterious, beguiling little flames. They flicker like candlelight in a drafty room. They burn through the dark hours, glittering in the raiment of night. Quenched by the radiant sun, they're relighted after sunset. They helped our ancestors count the seasons and find their way across a trackless world. Some people wish upon stars. Some people have feared or revered them. They seem eternal, but they're not. The stars we see with our eyes on a clear night are the same stars that our ancestors saw on their journeys within and out of Africa. But they saw some few stars which have since vanished from our sight. Stars, as it turns out, are temporary things. Just wait a few billion years, and the stars we see today will flare and then dim to darkness. Not to fret, though, for trillions of years hence, they'll be replaced by newcomers within the wheeling nimbus of our galaxy, and others as well. As we've learned on prior Science Sundays, our fate is intertwined with the lives of stars, certainly the sun, but also stars that no longer grace the nocturnal sky. Stars long gone were crucibles of creation. They smashed together primordial hydrogen and helium to create ever heavier elements. Elements such as carbon, oxygen, nitrogen, iron, and many other elements that don't end with the letter N. These elements are not only vital to us, they are us. We are literally bits of stardust, and except for the hydrogen in our molecules, we're star ash. We're temperate bits of metal glued together for a while into marvelous, temporary, sentient machines. We know that the universe is finite in time. There was a time about 13.8 billion years ago when the first atoms coalesced out of the tangle of energy and super heavy particles squeezed out of the massively energetic fields generated by the hot Big Bang. Those first atoms were hydrogen and helium. There was also, millions of years later, a moment when the first star, and then the second, and then billions more flashed into brilliance, illuminating a previously dark cosmos. Today, I want to tell you the story of these first stars, at least what astronomers think they know about it so far. And we will begin our conversation talking about the universe as we see it today, including the stars that we know that are collected in wheeling galaxies. And then from there, we'll talk about stars that came before and how they may be different than the stars we see today. Okay. So space-time. Einstein taught us important lessons about the relationship between space and time. In fact, I think the next Science Sunday that I do in 2 weeks from now, I think I'm going to talk about the amazing speed of light. Some of our insights into the way the universe works with regards to space and time came about by studying the properties of light. So I think I'm going to talk about particularly the speed of light as an amazing fact of nature next time. But we can talk about the universe as being represented by a span of space and time. The universe, in terms of the size it is today, from a certain relativistic perspective, the universe is about 92 billion light years across, and each light year is about 6 trillion miles. So 92 billion times 6 trillion miles across is what we expect the visible universe to be right now in terms of its geometric spatial extent. Also, the universe is known to be 13.8 billion years old, plus or minus a little bit. And we know that because of the science of the Big Bang, which I have talked about in prior Science Sundays. In this image, the arrow points to a galaxy. So in this swirling mass of dots and smudges, that is a galaxy. It's about 10 to the 58 times larger in volume than your house. Now, it's hard to grasp numbers like that, so here I've written it out for you. This is the number of times larger than a typical house that a typical galaxy is. Rather sizable. Well, it turns out that all of these other smudges in this picture are also galaxies. There are thought to be over 100 billion galaxies, perhaps even a trillion. They're hard to count, especially the further away and the dimmer they look to our telescopes. But there are certainly many, many galaxies.
Is this a composite picture, would you say, or is this an actual picture, maybe from the Hubble telescope? I mean, it's phenomenal to look and to see so many. I don't know if it was Photoshop to put so many in together of that size and nature. It doesn't give an image of a very empty space, right?
Yeah, this is a good question, Mike. This is called the Hubble Ultra Deep Field. And this picture was taken by the Hubble Space Telescope as it exposed its photographic sensors. They don't use film anymore, but like a sensor in a digital camera. It let light fall on that sensor, cumulatively speaking, for about, I think it's something like 22 days of continuous staring at a spot in the sky about the size of your fingernail, your pinky nail extended at arm's length. It gazed at a piece of sky about that big relative to the rest of the sky.
It might look actually blank to us, right?
Oh yeah, it would be completely dark to us and unremarkable. But if you collect enough of the trickling photons that come in one every hour or so, you do that for 22 days, you'll see some of these dim and distant galaxies in our universe. And you can do this by looking at any dark spot in the night sky, with a couple of exceptions where there's dark clouds of gas or bright swathes of stars intervening between our line of sight and the distant cosmos. But this is a real picture, not a composite and not a special effect.
And so when the light hits it for 22 days, you'd imagine with the Earth revolving and with all different things going on, that you'd imagine that it'd be fuzzy. It almost has to be maybe computer generated to clear up and put similar pixels or whatever into position.
Well, that's one of the great things about the Hubble and some of the space telescopes is that they can minutely control their attitude within space. You know, the angle that they're looking at. in the sphere of the sky, and they can maintain that with incredible precision over long periods of time. So the Hubble telescope, as it orbits the Earth, sort of stays pointing at a particular point, even though the whole telescope continues to orbit the Earth. So it's just fixed. And that isn't 22 continuous hours, but the telescope is capable of reacquiring that same geometric position with exacting precision over a course of perhaps 40 or 50 days, however long the total number of days was. All right.
So it doesn't get bothered by a cloudy day or anything like that?
Correct.
Like a cloudy day out in space?
Correct. So, you know, humans have wondered about the stars, their origin, and even their number for a very, very long time. In fact, an ancient book that some people turn to for a source of wisdom and even knowledge has in the book of Psalms a statement that the Lord God knows the number of the stars and has named them. Pretty profound statement. Well, you can do a little bit of a calculation if you want to count up the stars. So we can do something like our galaxy has 200 times a billion stars, and there are something like maybe 1 trillion galaxies all told. And you divide that number of stars by 13.8 billion years, which is 13.8 times a billion, times the number of seconds in a year, 3,154,000 seconds per year. Well, when you divide stars and seconds per year, and there's another year in that, so you get stars per second. So you're dividing stars by second years per years, which is just stars per second. So what this tells us is that given this estimate for the number of stars in our visible universe, how many stars you'd have to count and how long it would take you. Well, it turns out that in order to start counting from 13.8 billion years ago and to count every star in the known universe, give or take a couple, you would have to count 2 million stars a second since the beginning of the universe in order to fully enumerate the number of stars that are pretty much known to exist.
So that implies the creation of them occurred at amazing rates too, right?
Yes, yeah, right. Well, and that's sort of the next part of the story, is that the stars that we see today have not always been there. They have not been there since 13.8 billion years ago. But even setting that fact aside for a moment, just the number of stars we see in the sky today, 2 million stars a second since the Big Bang. So the rate of star generation has been furious for a long time.
They say things like more stars than there are sand pebbles or sand on beaches of all the beaches
Right.
of the world.
So when you look up at the night sky and see the starry night, one is inclined to ponder, where did we come from? Where did the stars come from? Were there first stars? Is there an oldest star? These are some of the questions that astronomers have asked. And for the first time in human history, only within the most recent generation of human beings have we begun to definitively be able to answer some of these questions. So this is a representation of the history of the universe on one slide. The universe started with the Big Bang, the big glowy dot there in the upper right. And then from the Big Bang, you had elements like hydrogen and helium that were generated from the potential energy fields, including something called the inflationary field, that dumped their potential energy into the energy of mass via E equals mc squared. In any case, soon after the Big Bang flared in incandescent heat, it cooled off. And all we had in the universe was a wafting gas of nothing but hydrogen, helium, tiny bit of measurable lithium, and then just a salting, a tiny, tiny salting of some heavier elements. But 99.9999 and several more nines% of all the stuff in the universe was hydrogen and helium. I think
Michael Pollack is saying, could you talk about the origin of light? And that's, I kind of wonder about that too. Was light available or around at that time? You'd think that this is maybe an era before photons and things like that.
Good question. So as to how light is generated, well, at a very fundamental level, light is generated whenever an electric charge is accelerated. But right after the Big Bang, it was hot because the universe was dense, and heat and the friction between atoms knocked electrons and protons loose from one another, and you had a plasma. And plasmas can be hot. A flame is a plasma. So the accelerating electrons and protons in the primordial universe made some kind of light. But subsequent to that, the gas in the early universe became so rarefied and so spread out by the expansion of the universe. And again, I won't go into detail about this. You can look up prior Science Sundays where I talk about the Big Bang. But the gas became so spread out that it no longer had collisions energetic enough to turn it into a plasma. So we had neutral atoms of hydrogen and helium. And neutral atoms like that, generally speaking, do not emit any light. So the universe, a few 100,000 years after the Big Bang, was black and dark, except for the leftover light from the primordial heat. What we see today is the cosmic microwave background. At one point, that was infrared background at the point that it was generated. But for a long time after the cosmic microwave background was generated by the heat of the early universe, the universe was cooling off and full of darkness. And what light could have been generated by occasional ionization events, etc., was quickly absorbed by the morass of other atoms. And the universe was literally dark for millions of years after the Big Bang had cooled off to infrared temperatures. And then at some point, on this diagram, it shows 400 million years after the Big Bang, the first stars came about. Well, this is sort of a dated picture, because now we know that the first stars were kindled into flaming existence about 180 million years after the Big Bang, not 400 million years. So again, observational evidence that has become available in the past decade or two has led to a refinement of our understanding about the early history of the universe, which is one of the most fascinating topics for many of us. So let's talk about first things. There was no such thing as the first life. Why can I say that with confidence? Because before anything existed that we might classify as biological life, there were replicating molecules, not organisms. So there's a continuum between replicating molecules and life, and that continuum mostly was played out billions of years ago in Earth's history. Similarly, there was no such thing as the first human. You didn't have suddenly an Australopithecus giving birth to a Homo sapiens. Biology doesn't work like that. Evolution doesn't work like that. It's a gradual process. So you would have a slow transition from hominids having particular characteristics and capabilities into a population, or several populations perhaps, of people that would be mostly indistinguishable from modern humans. So drawing a hard line and categorizing something as the first human being is just not only is it not possible in terms of going back archaeologically or paleontologically, but it doesn't make sense from a biological perspective. That's just not the way that things like continuums between species work.
Right, and not just hominids or life. You're probably making the point this is the same for rabbits or jaguars or
Right.
or fronds of ferns or different things like that as well too.
Yeah, it's a
I know
wonderful
Dawkins
continuum.
does an interesting discussion in his book about the what is it, the something tales? It's sort of
The ancestor's
the
tale.
ancestor tale.
Yeah.
In which he takes a rabbit back, and if you lined up all the rabbits and he chooses to go through a matriarchal line, each one would look very similar to its mother or have, very similar characteristics, but it would finally get to a point where it doesn't look at all, even though
The
it
one at the
looks
beginning and one at the end.
Right.
Right.
5,000 generations apart. You
Right.
can't really say that there's a rabbit, and I've talked about that in Science Sundays, where there's a Platonic ideal of not only a square or a circle, but of a rabbit or a horse,
Right.
which doesn't really fit in with the whole evolutionary frame of mind. And once Western thought started talking about Platonic ideals, it very much inhibits the capacity to talk about first stars
Right.
or people or rabbits or evolution or a lot of scientific concepts.
Yeah, many scientific concepts constitute continuums rather than discrete steps. But that's not the case for stars, surprisingly. Now, you can have stars of different sorts. You can have heavy stars and light stars and bright stars and dim stars and red stars and blue stars. And those colors and masses can exist along a continuum. But there was a first star in the universe. Now, it's unlikely that scientists will ever be able to spot it, literally speaking, and it has long since vanished from the cosmos. But logically, practically, according to physical and natural law, there would have been a first star in the universe, and it was a brilliant blue star. So let's get into Act 2 of our drama, Generations of Stars. One of my favorite Shakespeare quotes.
Yes, Horatio.
You want to do this one, Mike?
I don't know if I have the English accent, but I know that is it in Hamlet?
It's in Hamlet, yes.
Yeah. There are many things in heaven and earth, Horatio, that are dreamt of in your philosophy.
And more things.
There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy.
That's right. This is often used to keep scientists humble. The universe is full of surprises. And over the past several hundred years that the human race has been serious about the study of astronomy, we have encountered surprise after surprise. And Shakespeare would not have been surprised by that fact.
Mm-hmm.
So there was this famous astronomer, Annie Jump Cannon, who lived from 1863 to 1941, and she classified and cataloged stars. This was her job. And she was really good at it. And she detected patterns and similarities and disparities between different sets of stars and was able to group them. And she grouped them in such a way that a couple of subsequent astronomers came along, and I'm trying to hit the forward here on my remote. There it goes. And Hertzsprung and Russell in the early 20th century, two different astronomers, plotted the luminosity versus temperature. Do we have good news, Mike?
Just nothing special. They're heading to the hospital. Initial slight contractions. And they
Okay.
all seem ready to start.
So we've got luminosity versus temperature for stars, and also represented on this particular plot are relative sizes of stars. And in this, our sun would be, you see where the letter G is, and right above it there's some little yellow dots?
that would correspond to the location of our star on this diagram. The big sort of sidewalk in the middle of the diagram made up of a lot of little dots, that's called the main sequence. And the cool physical thing, the nifty physical thing about the main sequence of stars is that those stars are burning hydrogen as their nuclear fuel. Well, once a star runs out of hydrogen, it may start burning other elements like helium, eventually carbon and nitrogen, etc. But for the bulk of a star's life, the bulk that it burns with nuclear fusion is hydrogen. And Annie Jump Cannon helped pave the way for the discovery of that path. This is a picture of a star that you may have seen in the past. It shows schematically the layers of elements within a very mature star. In fact, this star is very near, if not right at the end of its life. It started off burning hydrogen, and some of the leftover hydrogen remained in an outer envelope surrounding the bulk of the star. And then within that was helium. And so as you're going down towards the core of this onion-like star, what you're finding is heavier and heavier elements that at one point were being synthesized by stellar fusion into elements that allowed for the liberation of energy. So when you get almost all of these elements, when you're hot enough to smash them together so that they stick and form a new element, even though it takes a great deal of heat and energy to make that fusion happen, it releases more energy than it took, which is one of the reasons that humanity is pursuing fusion power. Ideally, at some point, we might develop technologies capable of smashing atoms together and making them stick, but in the process of sticking, they would release more energy than it took to smash them in the first place. And this all works fine until you get to iron, and actually nickel as well, a certain isotope of nickel. But once you get to iron, especially, when you smash iron nuclei together, it takes more energy to smash them together than they liberate once they've glued. And so at the juncture when a star accumulates iron in its core, the star dies, and it stops generating heat from nuclear fusion, and that can cause the star to catastrophically collapse onto that iron core and then potentially rebound in an explosion that we call a supernova. So that's kind of the typical view of a star. Now, our star, the sun, and several other stars like it are not nearly heavy enough to generate enough pressure and heat in their core to create iron and silicon, but they can eventually produce a certain amount of nitrogen and oxygen and carbon. Star formation. This is the first point I want to make. When stars form, they form these swirling eddies of gas and dust, although the first stars in the universe would not have had any dust available. When astronomers speak about dust, they're speaking about literally little tiny bits of ice or little balls of carbon, other molecular remnants from prior generations of stars. But the first stars in the universe just had hydrogen and helium to work with. But they still created stars in a similar way. Gravity would pull the matter in towards a common center, and as the matter swirled in, it would, conservation of angular momentum would flatten it out into a disk. And then in the center, you'd have a baby star forming. And this baby star would be full of ionized gas. And remember, ionized gases, ions, are electrically charged. And a moving electric charge swirling around a star, moving electric charges, one of the things they do is they create magnetic fields. Well, the tangled magnetic field near the baby star would allow for the formation of stellar jets. And here's a picture from the Hubble telescope of one of those stellar jets. It's called a Herbig-Haro object. I may not have pronounced that correctly. Apologies if I mispronounced it. But this is a Hubble telescope image of, there's a, right in the middle of the picture where that little knot of gas and dust is, buried deep inside there is a baby star. And that star is ejecting matter along its magnetic poles because the matter swirling around it, being sucked in from that gas cloud, is ionized and creates a magnetic field. Here on the next slide is a couple of time-lapse movies about the way these jets propagate through space. So, star formation point 2 I want to make is about something called the Jeans length.
Can I jump in here? There's a
Okay.
question about star formation. And
Sure.
Michael again says, so with all these dramatic readings, is everyone really watching 2 other new stars being born today? You and I with our dramatic readings of Shakespeare.
Oh, I see what you're saying.
He's,
Yeah,
It's
I,
his-
I think you have the natural charisma necessary to become a star.
yeah,
I'm sort of a
I just have to
nerd.
swirl a little faster
Yeah.
maybe, or, yeah.
Get a couple of jets, high-energy jets, maybe New York jets, I don't know.
I was thinking that I shouldn't blow my line and read many instead of more. I always thought that had a different way. There are many more.
Yeah, well, even professionals require a second take
Yeah,
sometimes.
and care with a prop gun too.
Yeah, oh my goodness.
Too soon?
Yeah, too soon. All right, so I want to talk about something called Jeans length and also Jeans mass.
Oh,
Now, Jeans was just the name
is
of
that a selfie?
I'm not going to talk about that. The notions here, that's just the name of a person, and the jeans length and the jeans mass are not about clothing. Instead, they're about something like this. When a cloud of gas and/or gas and dust grows, it gets hot because the particles in the gas are colliding with each other and perhaps bleeding off some heat energy. Well, there's a balancing act between the force of gravity that wants to crush the cloud down and the heat generated by the friction in the cloud, which gives velocity to the gas and keeps it from tending to collapse. So this fine balancing act between the force of gravity and the heat is not just relevant once you have a star, but it's also relevant to the clouds that collapse to form stars. And it depends critically on the atomic mass of the elements. So if you've got a heavy element, imagine hitting a bowling ball with a BB. The bowling ball is just, it's not going to do anything. But if you hit a BB with another BB, and both of them go zooming off, and they remain high velocity particles. But the energy imparted to a bowling ball by a BB, it's the same amount of total energy, but the motion is trivial. And one of the implications of this is that heavier elements are able to absorb more energy and allow a cloud to cool down faster. Whereas if you have a cloud, a cosmologic, astronomical scale cloud built of light elements, it tends to get a lot hotter as it tries to balance the force of gravity. And if it gets to the point where it has enough mass, it can still collapse to the point where it starts forming stars. But it takes a lot more matter of just hydrogen and helium to instigate that collapse than it would if there were heavier elements mixed in. So the stars that we see around us today in the universe are called population 1 stars. And they were generated about anywhere from 10 billion years ago till the current day. Our star is about 5 billion years old. But this population of stars can trace their lineage back to about 10 billion years ago, which is almost 4 billion years after the Big Bang. So what happened in those prior 4 billion years? Well, here's some facts about today's generation of stars. They include metals, the heavy elements. So in an astronomer's lingo, a metal is anything heavier than hydrogen and helium. So carbon, nitrogen, silicon, sulfur, praseodymium, xenon, all of these things are metals in astronomer speak. I guess.
Maybe Scott, can you blow this picture up or take the whole screen up with this picture? It's fascinating picture.
Yeah, I got some bullet points to work through on this. You can just make it sort of, fill up the whole screen. So the initial size of the stars and the clouds that formed them was limited by the metals that absorbed a lot of heat energy. The stars that we see around today incorporate a significant amount of dust and ash from older stars that shattered previously and blew apart. And stars with a noticeable amount of iron and other heavy elements constitute population 1 stars. So our sun has iron in it. Small amount, but noticeable. And the kinds of stars that are being born today, because they're born out of clouds that have things like silicon and aluminum and iron and oxygen, etc., they're also capable of forming solid planets that accumulate in eddies around that protostellar disk.
Did they detect this heavier elements with spectroscopy or?
Yeah, you can look at a star and see what elements are inside of it and what their proportional amounts are. In fact, about 3% of our sun is things besides hydrogen and helium. And this is relative to the way stars incorporate elements. This is a big number. 3% of the matter in our star is iron and carbon and nitrogen and silicon. And that matter was not generated by nucleosynthesis inside our star. That's material that was in the interstellar cloud of dust and gas that collapsed to form our star.
It's still not forming elements in our star?
Our star is forming helium right now, and an absolutely trivial and ignorable amount of maybe carbon, nitrogen, and oxygen through something called the triple alpha process. But that, by far, the major way that our sun liberates energy is by just smashing hydrogen together. It's in the main sequence. Well, before our sun existed, and contemporaneous with our sun, is a different sort of star that has anywhere from 10%, and some stars have been found that only have 1/250,000th of the metal abundances that our sun has. So there's still a detectable amount of things like iron and silicon and nitrogen and carbon, especially nitrogen, carbon, and oxygen in some stars, but it's incredibly depleted compared to what we call population 1 stars. And these are the oldest stars we've observed directly in the universe. And some of these stars we can see so directly that we can focus a telescope on them. They're still around. Especially some of the lighter stars. The lighter it is, the longer it lives, paradoxically. The bigger it is, the shorter it lives. So if you look at a globular cluster, which is a ball of stars that orbits our Milky Way in a very elliptical orbit that's kind of like a rubber band stretched between two widely separated fingers, so they orbit kind of like this and pass through the galaxy. These globular clusters have a lot of these population 2 stars in them. But these stars must have formed after a prior generation died, because these population 2 stars, even though they have a minuscule amount of heavier elements, they have some. So they're not just balls of hydrogen and helium. And as I said, many of these sorts of population 2 stars are still visible in our universe today. And they have a lot of materials that derive from the alpha process, which I briefly mentioned, and I won't go into detail about that in the honor of time. So there must have been first stars, the oldest stars in the universe, that were nothing but hydrogen and helium, tiny amount of lithium. And these are called population 3 stars. Now you may think that the first generation of stars should be called population 1, and the second generation population 2, but that's not how we started counting. We started counting by looking at the stars today and saying, population 1. And then population 2 are the older stars, and then hypothetically we have these population 3 stars. Now, why do I say they're hypothetical? Because detecting them is really a challenge, and I'll talk more about that in just a minute. But these stars have zero what's called metallicity, no enrichment with higher numbered atomic elements beyond hydrogen and helium. Some scientists argue all of these first stars were gargantuan behemoths and very short-lived. Or, to honor Shakespeare, very short-lived. They frequently exploded as supernovas, and not just any sort of supernova. I'll talk about that in just a second as well. And one of the things that these first big, brilliant, bright, shining stars did was the leftover hydrogen and helium, which had not collapsed into stars, which was by far most of the hydrogen and helium still in the universe. Well, these first stars were so brilliant that they ionized the gas. And I've talked about that again a couple times today. Strip off the electrons from an atom, and you're left with charged particles, ions. So these first stars were bright enough that they actually ionized what had previously been the neutral atoms of hydrogen in the universe. Now, one of the things about hydrogen, when it absorbs a little bit of energy, is when it releases that energy and relaxes down to a lower energy state, it emits light. And one of the characteristic types of light is called 21 centimeter, and that's radio wavelength, 21 centimeter light. And I'll explain that in much more detail in just a minute. So these stars are expected to have formed somewhere around 100 billion to 200 billion years after the Big Bang, the hot Big Bang, had commenced. The hydrogen and helium in the universe were not blue. Hydrogen and helium don't have a blue color. But the first stars were blue. In fact, they were so blue, they were mostly ultraviolet. They were called blue supergiant stars, only hydrogen and helium. Super large and massive, expected to have been from 10 to 300 times the mass of the sun, and UV light. Here's a comparison between our sun and what these stars were expected to have been. Gigantic balls of energy derived from the fusing of just hydrogen and helium. But incredible amounts of energy released. Remember, the larger, the heavier the star, the quicker it burns out. So these stars were also very short-lived, a lifespan of only perhaps 2 to 3, 5 million years, depending on the specifics of the mass in the particular star. One of the ways that these stars ended their lives is in something called a pair instability supernova. This is a type of supernova where it gets so hot in the center of these gigantic stars that it's hot enough to accelerate the plasma to release gamma rays. And these gamma rays, because, again, thanks to our trusty E equals mc squared, gamma rays have enough energy to, I'm taking a couple shortcuts here, but to split into a positron and an electron. Well, when that happens, instead of having a hot, high-energy gamma ray trying to get out of your star, now you've just got electrons and positrons, just little particles of matter. Well, this actually cools off the core of the star catastrophically. Well, remember, when a star stops generating heat in its core, gravity wins and smashes it down. And the reverberating sonic boom from that sudden catastrophic collapse due to a pair production completely obliterates these stars. They don't leave behind a neutron star. They don't leave behind a white dwarf or a black hole. Some of these things you may have heard about. They completely obliterate themselves. And in the process, spread especially carbon, hydrogen, and nitrogen. which were some of the main products of nuclear fusion that they made. And that's the reason we find population 2 stars having an abundance, relatively speaking, an abundance of carbon, hydrogen, and carbon, nitrogen, and oxygen compared to some of the heavier elements in the cosmos like silicon and sulfur and iron and whatnot. It was like this pair instability supernova was likely the fate of most population 3 stars. It required low metallicity to begin with, otherwise these pair production supernova events could not have happened, and they required enormously massive stars, completely obliterating the star, leaving behind the carbon, nitrogen, and oxygen.
Is there any evaluation by astronomers of how many of these there were, 300 or 300 million, or?
I have not read an estimate of the number. There may be such a thing, but I have not encountered an estimate of the number of such stars. The most massive population 3 stars collapsed into black holes, so they were massive enough that when their heat turned off and gravity took over, they didn't have time to rebound in a shock wave to create a supernova. They could have immediately turned into black holes. And maybe these were the seeds of galaxies.
Because they
in
had
subsequent
gravity, and even though they sent out massive amounts of particles, of elements, they would.
These did not send out massive amounts. So that's the difference. If you get a high enough mass in your star, when the heat of the center of the star turns off, gravity is so powerful and the collapse is so sudden that it just turns into a black hole immediately without exploding at all, without leaving any trace. So either the first stars obliterated themselves completely, or they completely vanished. 2 extremes. And so searching for evidence of both of these phenomena is something that astronomers are interested in. Now, in terms of looking for the first stars, one of the things we could do is search places where we know there are older stars as a predominant population of stars compared to the other stars nearby. In the galactic disk of the Milky Way, etc., new stars are constantly being born. It's not a good place to look for ancient stars. The signal to noise ratio would be terrible. But in the halo, this glowing nimbus around our galaxy, there's the potential of having old stars. And that's where, indeed, we find a lot of population 2 stars. As I said before, we also find a lot of population 2 stars in globular clusters. There's also something in our universe called ultra-faint dwarf galaxies that might also harbor really ancient stars. Now, one of the things some astronomers speculate about is that instead of forming little eddies where you had planets around the first supergiant stars, maybe some of those little eddies turned into smaller stars with masses less than the sun. And those could be long-lived enough to persist to the current day, but they haven't been found yet. So we can look at globular clusters for population 2 stars, perhaps find some relic population 1 stars if they are low mass and haven't burnt out yet. And then, as I said, none have been found. So you don't have to read these. I've already said all of this. Searching further away for the first stars. One of the things we can do is look at the distant universe. We literally see the universe in the far distance as it was when it was much younger. So we can use gravity as a lens to magnify the light of very distant galaxies and see what the spectrum of light tells us about them. And so far that also has not directly detected the light of these purported first stars. So let me talk a little bit. I'm rushing through this because we only have a few minutes left. We've got neutral hydrogen atom. Protons and electrons have something called spin. If their spin is aligned, it's like having 2 magnets with their north poles aligned and trying to bring them together, and they don't want to do it, they want to flip. Well, the same thing happens with atoms. The spins of a proton and an electron in neutral hydrogen want to flip. And so it takes energy to keep them back in this more elevated energy state. And whenever it transitions from a higher energy state to a lower energy state from this electron flip, it emits this 21 centimeter light. So in the early universe, this flipping was constantly reinvigorated by the leftover heat from the galaxy. 21 centimeter light corresponds to a pretty low temperature. So we can detect this flipping of the electron states in the early universe because of the direct effect of the cosmic microwave background. Well, once the first stars formed, it really got things going in terms of energizing the hydrogen atoms. And the net effect of this was that the gas around these stars could actually absorb more energy because it was hot, so trivial amounts of energy such as would be generated through an electron flip was just lost in the noise, and you just don't see it. The other thing to know about this is that because of the expansion of the universe, the 21 centimeter light from 180 million years after the Big Bang has been stretched to 4.5 meters, and from 280 million years after the Big Bang to 3.3 meters. So what we can do because of this stretching is we can build some radio telescopes to look for this particular radio signal of the light from the era of the first stars. So you might think that we build a giant radio telescope like this. We don't. Instead, some scientists from MIT and other places, a small handful of scientists, built this thing about the size of a dinner table. And this is a radio telescope set in Australia. And the meshing on the ground is to absorb radio waves and cut down on the noise. And this is part of what's called EDGES, Experiment to Detect the Global Epoch of Reionization Signature. So when the first stars ignited, they ionized the hydrogen. I think I've mentioned that a couple times. And you can detect that by looking carefully at this 21 centimeter radiation. So we've got the cosmic microwave background represented by the dotted line at top. You've got the first stars turned on about 180 million years after the Big Bang, and then by 270 million years after the Big Bang, they had ionized all of what had previously been neutral hydrogen in the universe. And this radio signal has, as of 2018, been detected for the first time. Direct evidence of the action of these first stars on the properties of the interstellar gas that existed in the universe at that time. We haven't actually seen the stars themselves, though. The other thing is that this is a bit deeper. The amount of absorption is a little greater. People are speculating that maybe this is because of dark matter, or maybe just the experiment wasn't sensitive enough or had some flaws or systemic errors and whatnot. But the little tiny wiggles in this, if we could just resolve those wiggles, they may tell us something more interesting about the universe. Well, the fault, dear Brutus, is not in our stars, but in ourselves and in our instruments. Future instruments, like a lunar orbiter satellite, Dark Ages Radio Explorer, might do a better job of resolving some of the wiggles in that signature of the first stars. And then also, you'll notice down at the bottom panel, the little red shaded area, that really zooms in on that dip in the radiograph. That's what this telescope, which is going to launch in 2023, I think, is scheduled to zoom in on. Perhaps a bevy of red dwarf stars exist that we can detect, but they would be really dim. And then finally, the James Webb Space Telescope may see the dim and red-shifted light of pair instability supernovas in the distant universe, and they may see the light of population 3 stars directly as dim infrared signatures. So the James Webb Space Telescope will help us find evidence about the first stars. And I think that's it. That's all I had for today. Here's a couple of books that I used to inform this talk. The first book, the book on the left, is not quite as technical as the second one. The second one is not so technical that you need a lot of math to understand it, but it goes into more detail about things like the 21 centimeter hydrogen emission line and whatnot. So I recommend both of these if you're interested in the story of the first stars. And we are out of time. I have to stop promptly at 1. If you have questions or comments, please feel free to type them into the comments section, and they will show up on YouTube, and I'll check this out later and answer the questions. Give us a thumbs up, subscribe, check out the Prairie State Humanist Meetup page for further announcements of future events, and we'll see you in a couple weeks.
Yeah, I think there's another meeting now of
Right.
So you wanted that, you were kind of constrained on time today.
Right.
So we won't take questions now, but send comments in, and thank you very much. It was a great talk, very good. I loved the tie-ins with Shakespeare and
Good.
so on too. So I will work on my presentation of Shakespearean drama.
That'd be nice to see.
Yeah, good.
Good luck on the baby,
Thank you.
grandbaby. All right, take care, everyone. Bye-bye.
Bye.